Recording start.
Okay, assalamu alaikum.
Walaikum assalam, sir.
How are you?
Fine, sir.
All right. Okay, we start this lecture of function analysis. This is fifth lecture of the course. Today is December 12, 2020. If you remember, in our previous lecture, we defined sequence, convergent sequence, Cauchy sequence in nonlinear spaces. And then we proved some result. Today we shall define, inshallah, bounded linear operators on normed linear space. You know that a map from one set to another set is called function, whereas a map from one linear space into another linear space is called an operator. Right? This is the difference between function and operator. Function is defined between two spaces, sets, whereas operator is defined between two nonlinear spaces. In the slide, you can see that if x and y are linear spaces or the same scalar field, and A is any map from the domain of x into a range in y, then this map is called operator. And by definition, this operator is linear if it satisfies the following two conditions. First condition is that domain of A, that is domain of the operator A, is a subspace of X. And the second condition is for all x1, x2 in the domain of A, and then a scalar alpha, this first condition, the image of x1 plus x2 under this operator is equal to image of the first element plus image of the second element under this operator. Secondly, if we multiply the element x of domain of A by a scalar, that is, it is the scalar multiple of x1, its image under this operator is alpha times image of x1 under this operator. If these two conditions are satisfied, then we say that the operator is linear. And the condition B can be written in this form as well. A alpha x1 plus B plus beta x1, x2 is equal to alpha ax1 plus beta ax2. You can write those two conditions for the linear operator or this single condition. These conditions are equivalent. If domain of A is contained in X and range of A is contained in Y, then this is an operator from domain of A onto. Please remember this onto. If domain of A is contained in X and range of A is contained in Y, then the operator is called onto operator from the domain of A onto range of A and written as A from domain of A into range of A. So remember this word onto. Right? Or when this operator is from the domain of A into the range, to the whole range space Y, then it is called into. Now you see here, this is, in the first case, A is a map from the domain of A into range of A, where domain of A is contained in X and range of A is contained in Y. But when A is an operator from the domain of A into the whole space Y, then it is called into operator. And when this domain of A is equal to the whole space X and range of A is the whole space Y, then we say that this operator is from X into Y and written as A from X to Y. You are already familiar with the definition of operators. Or if you remember, you have studied this in BS, where you call this as a transformation. Operator and transformation, these terms are synonymous. They have the same meaning. Now, one remark on this definition. Now, you see that these are remarks, small results, which follows from the definition. It follows immediately from the, by induction, 1 and 2 in condition B of the definition, that A applied on alpha 1 x1, alpha 2 x2 plus alpha n xn. This can be written as alpha 1 x1 plus alpha 2 x2 plus alpha n xn. So it means that by induction you can generalize this second condition in B to n elements. If alpha is 0, by second condition of B, we see that A0, that can be written as A times 0 into alpha. And then by linearity of the operator, you can write this as 0 times AX, which gives you the image of zero element or vector in the linear space is 0. So remember that the image of 0 element under a linear operator is always 0. So it's a small result which follows from the definition. This remark C, it says that A applied on minus X. Again, this can be written as A times minus 1 into X. And then by definition, second condition of B in B, you can take out this scalar minus 1 outside, and inside you are left with AX. So A minus X is equal to minus AX. This also follows from condition B of the linear operator. And this D, an important subset of the domain of A, where this A is operator, is the null space of A. Now, how do we define null space of any operator? It is defined as the set of all X in the domain of A such that their images under A is always 0. So null space of the operator A is the set of all X in the domain of A such that Ax is equal to 0. And you can easily prove this result to show that null space, which is also called kernel of A, it's a subspace. And when a set is a subspace, you know that a set is a subspace if it satisfies two conditions. The first one is that it must be closed under addition, and second condition is it must be closed under scalar multiplication. So in order to prove that null space of A or kernel of A is a subspace, you have to check these two conditions. If these two conditions are true, then you can say that this null space of A or kernel of A is a subspace. So this is one result which you can prove yourself easily. Some examples of linear operators. Identity operator. What is identity operator? It is an operator from X into itself. I from X to X means domain space and range space are the same. Identity operator is defined as the image of any element X in X in the domain space is equal to X for all X in X. So considering any element in X, its image will be equal to itself. If this property is satisfied by some operator or map or transformation, then it is called an identity operator. Zero operator. What is zero operator? It is a map from one linear space X into another linear space Y defined by Tx, that is the image of any element X in the domain space is 0. If you consider X1 in X, its image will be 0. If you consider another element X2 in X in the domain space, its image will be 0 and so on. So if this condition is satisfied by the by the operator, then such an operator is called zero operator. And zero operator is also called null operator or trivial operator. So instead of this zero, you can use null or trivial. So zero operator, null operator, trivial operator, they have the same meaning. Third example. These two are very simple examples of linear operators. You can easily check that this identity operator and zero operator satisfy the two properties of linearity. That is, Tx1 plus x2 is equal to Tx1 plus Tx2, and T alpha x is equal to alpha times Tx. These are two properties of linearity. And you can easily check that identity operator and zero operator, these two are linear operators. This third example, consider the linear space X of all polynomials. This means that every element of the linear space X is a polynomial with real coefficient defined on the closed interval 0, 1. That is, D is a map from X into R, where each element of the domain space is a polynomial instead of any vector. It is defined by dP is equal to derivative of P with respect to derivative of X. If this D, which is a map from 0 to 1 into R defined in this way, then this D is also a linear operator, because on the right hand side you have this derivative. And do you know that differential operator is linear? So it is clear from the definition that this D satisfies the two properties of linearity. If you remember, if you don't, listen carefully. that integral operator and differential operator both are linear. Let me recall. You know that integral of c f of x is equal to c times f of x, where c is a constant. And you also know that integral of function f plus g is equal to integral of f plus integral of g. So this integral satisfies the two conditions. So, and similarly, the differential operator also satisfies these two conditions. So this d from the domain space X, which is the space of all polynomials defined in this way, is a linear operator. Next, the mapping T from C0, 1. You are familiar with this linear space. This is the space of all continuous real valued functions defined on the closed intervals 0, 1. In this way, that is, Tf is equal to integral from 0 to 1 f of x dx. It's a positive integral. As I said, that integral is linear. So the right-hand side satisfies these two conditions. So this T, which is a map from the set of all defined on the set of all real valued, continuous real valued functions, is also a linear operator. So these are some simple examples of linear operators. And please check the two conditions of 1, 2, 3, and 4 just for practice. There is no doubt these 4 operators will satisfy the two conditions. And do this, please, yourself at home. We move to the next slide. Like a function, you know that function is a map from one set into another set. And sometimes we say that this set is 1 to 1. Sometimes we say that this set is onto. And sometimes we say that this set is, function, not set. This function is 1 to 1 and onto. Similarly, an operator can be 1, 1, can be onto, can be 1, 1 and onto. So these are the definition of this 1, 1 onto and 1, 1 and onto operators. Now come to this first definition. Definition A mapping T from the domain of T in X into the whole space Y is said to be injective or 1 to 1. If different points in the space, in the domain space, have different images. That is, if we consider any two elements, x1 and x2 in the domain dt, and they are distinct, that is, x1 is not equal to x2. Both x1 and x2 belong to the domain of T, and this implies that their images are not equal under this operator. Then the operator is, or the mapping is, or the transformation is 1 to 1. If the images of two distinct elements in the domain spaces gives you distinct images, then we say that the transformation or operator is 1 to 1. And we say that a mapping T from the domain of T in X into Y is surjective or onto if the range space is equal to the whole space Y, right? A mapping T from the domain of T in X into Y is said to be surjective are onto if the range space, this is the range space, range of T is the whole space Y. Remember that range of any map is not always equal to the whole domain range space or range set. It is in most cases a subset or subspace of the domain space range space Y. But if the range of the operator or the function is equal to the whole domain range space or range set, then we say that the function or operator is onto. And if the operator T satisfies the both condition A and B, that is, it is one-to-one and onto, then it is called bijective. So the definition is the same, which is for the one-one onto and one-one and onto function. The same definition, no difference, right? So remember this definition when a map is one-to-one, when it is onto, and when it is bijective, that is one-to-one and onto. No one notation, you are already familiar with this notation. If A is an operator, its inverse is denoted by A power minus 1. This is the notation for inverse of the operator. It's not something new. You are already familiar with this, but simply to recall your memory, how do we denote the inverse of an operator? It is denoted by A power minus 1. If A is an operator, then this notation is the notation for inverse of the operator. One theorem, we state this without proof because it has been taken from the algebra. You are already familiar with this result. It says, let A be linear operator or linear transformation, then its inverse is also inverse exists if and only if this condition is satisfied. That is, the image of any element x under A is equal to 0, and this gives you x equal to 0. If this condition is satisfied, then we say that the inverse of the linear operator exists. And when this inverse of A of the operator A exists, then this inverse is also linear, right? So this result says that if inverse of an operator A exists, means satisfying this condition, then this inverse of the operator is also linear. Now we state another result, which is this result. You know that if T is an operator from one linear space into another linear space, means from the whole space X into another whole linear space Y, then this, the inverse of this operator exists when, if and only if it is one-to-one and onto. And in most cases, you use this definition. You know that when an inverse of a function exists, we say that an inverse of a function exists if and only if it is one-to-one and onto. Same is here. And in the previous result, T was a map from the domain of T in X into Y, not from the whole domain X, but from the domain of the operator in X into the whole space Y. In that case, inverse of A exists if Ax equal to 0 implies that X is 0. If this condition is satisfied, then the inverses exist. And here, in this example, if T is an operator from the whole space X into the whole space Y, then the inverse of this operator exists if and only if it is one-to-one and onto. So these are some definitions which we shall need in our later work. So please carefully look at these definitions and remember this, because we shall be using this result in our later work. All right. Like a function. When function is continuous. Similarly, we can say when an operator is continuous. Definition of continuity for the operator is exactly the same as definition for continuity of a function. Because you know that an operator is also a function. But function is not always an operator. Why? Because function is defined by between two sets, whereas operator is defined between two linear subspaces. And what are linear spaces? Linear spaces are basically sets satisfying some additional conditions. So linear space is a set, but set is not a linear space unless it satisfies the additional conditions. So operator on the map defined on linear space can be called function defined on the linear spaces. So linear space is a function, but function is not an operator. So the definition of functions can be carried over to linear spaces. डिफिनीशन में कोई फर्क नहीं है, सेम डिफिनीशन जो लीनियर फंक्शंस के लिए वही लीनियर ऑपरेटर्स के लिए भी है. Like this first one, when an operator is continuous at a given point, and when it is continuous, we say that X and Y are nonlinear spaces over the field K. We have already mentioned this K in the beginning of our course, that throughout this course K will denote the scalar field. It could be either real or complex. So this K denotes both real and complex scalar fields. And let T be an operator from nonlinear space X into a nonlinear space Y. Then we say that T is continuous at a given point X naught in the domain space X if for any epsilon positive there exists delta positive such that Tx minus Tx naught norm is less than epsilon whenever X minus X naught norm is less than delta. Now you see the same definition which we have already defined in real case. Over there we take norm instead of this, absolute instead of this norm, here and here. And instead of T, we take f of x minus f of x absolute is less than epsilon whenever x minus x naught is less than this delta. So it's the same definition. We say that an operator T from a nonlinear space X into a nonlinear space is continuous at a given point X naught. If for any epsilon greater than 0, there exists delta greater than 0 such that Tx minus Tx norm is less than epsilon whenever x minus x naught is less than delta. And we say that this operator is continuous if it is continuous at every point of the domain space x. यहाँ पे हमने एक पर्टिकुलर पॉइंट लिया हुआ था. We say that this operator is continuous at this particular point x naught if this condition is satisfied. And if this condition is satisfied for all elements in the domain space, then we say that the operator is continuous. Simply say continuous. We don't mention the point because it is continuous at every point. So if it is continuous at every point, we say that the operator is continuous. And there is an equivalent definition of continuity. As I told you in the face-to-face class, if a function f is continuous, if xn converges to x implies f of xn converges to f of x, then the function is continuous. So this is an equivalent definition. Similarly, an operator t is continuous on x if for any sequence xn in x such that xn converges to x implies t of xn converges to t of x. If this condition is satisfied, we say that the operator is continuous. So you can use this delta epsilon definition or this condition. But in practice, we use this second definition to show that given operator is continuous. We consider a convergent sequence xn converging to x, and we have to show that txn converges to tx. If we could show this, then we say that the operator is continuous. So in most cases, we use this later definition of the continuity of an operator. And this third definition, we say that t is continuous at the origin. When? If and only if xn is a sequence converging to x to 0, implies that txn converges to t0. And you know that just in अभी हमने remark में कहा that image of any of 0 element under any operator is 0. So you can write this t0 as 0. So the definition becomes an operator t is continuous at the origin if and only if